Compound characterization, mass spectroscopy. At the end of the Introduction to Spectroscopy webcast, which you viewed last week, we discussed what kinds of information we need in order to identify an unknown compound, such as that mysterious white powder in that webcast. To identify an unknown compound, we need to know what atoms make up that compound, what building blocks are available to us, and it would be useful to know if there were any functional groups, common combination of atoms that are present in that molecule. Once we have that information, we can then begin trying to see if we can figure out how all of those pieces are connected in order to identify the structure of our unknown compound. In order to gain that information to answer these questions, we use spectroscopy. Today, we are going to see how mass spectroscopy allows us to answer this first question: what atoms make up our mysterious compound? Using modern techniques, mass spectroscopy allows us to determine the molecular weight of our mysterious compound. On the right side of the screen here, we have a general schematic of a mass spectroscopy instrument. How a mass spectroscopy experiment works is you take your analyte, the compound you are analyzing, and you convert it into ions, here in the ion source. You take your sample, you inject it into the instrument, and then the instrument converts it into ions. These ions are then sent into an area containing magnets. These magnets then filter these ions. How do magnets separate ions? Magnets generate a magnetic field. These ions are not magnetic. So what's happening here? Remember from physics that when you have a magnetic field, you also have an electric field. Using these magnets, we can create a magnetic field which creates an electric field, which allows us to filter out the ions we want. This filtering process separates ions based on their mass to charge ratio, which on this screen is designated by m/q, where m is the ion mass and q is the ion charge. There are a few other letters which can be used to signify ion charge. In this presentation, you might see E, used to represent ion charge. You also might see the letter Z, used to represent ion charge. These three letters, Q, E, and Z, all mean the same thing. The instrument can then tell us what mass to charge ratios are present using a detector. We then know what kinds of ions were made in our sample. You do not need to memorize this schematic. You do not need to know all of the pieces of a mass spectrometer. You simply need to know the basic components. You have an ion source that makes ions. These ions are then sent into an area containing magnets. These magnets then sort, separate, filter out the different kinds of ions, and they do so using the mass to charge ratio. If our detector detects a particular mass to charge ratio, it lets us know via the spectrum output. There are two general methods to turn our sample into ions. The first way is to use what is called hard ionization. Electron ionization is an example of a hard ionization process. Hard ionization deliberately fragments our molecule using force. In the case of an electron ionization process, we take electrons and we shoot them at our molecule. These electrons hit our molecule and then break it into many pieces. Based on what fragments our detector sees, we can then learn what pieces are present in our molecule and try to put it together. On the cover of your laboratory notebook, there is a mass spectroscopy section which lists several common fragments and their associated masses. For this course, we will not focus very much on hard ionization techniques. Do not memorize that table of fragments. Know what hard ionization is, know the basics of how it works, and know what kind of information it gives us. The second type of ionization is called soft ionization. An example of soft ionization would be electrospray ionization. Soft ionization takes our molecule and it turns it into an ion, but it doesn't fragment the molecule in the process. This type of information is useful because it allows us to find the molecular formula of the molecule. Because our molecule is kept intact in one piece, we can discover its molecular formula. On this slide, we see the structure of acetylsalicylic acid, better known as aspirin. Aspirin has a molecular weight of 180 grams per mole. However, as is, aspirin is not detectable on a mass spectrometer. Remember, mass spectroscopy requires your compound, your analyte, to be converted into an ion. How electrospray ionization accomplishes this is it takes the molecule and it attaches an ion to it. There are many ions that are available, but the two most common ions are the hydrogen ion, shown here as H+, and the sodium ion, shown here as Na+. Before we continue, first some terminology. You may hear me refer to the hydrogen ion as a proton. This is organic chemistry parlance. We call a hydrogen ion a proton because if you take a hydrogen atom, which contains one proton and one electron, and you remove that one electron to make it into an ion, all you're left with is a proton. You will hear me use this terminology again when we begin discussing nuclear magnetic resonance spectroscopy. Recall that our mass spectrometer detects a mass-to-charge ratio, not simply mass. Fortunately for us, electrospray ionization tends to make ions that contain only one charge. For this course, if I give you a mass-to-charge ratio, you can safely assume that the charge is 1. As a result, if we were to take these combinations of aspirin and these ions and combine them, we would expect to see a mass-to-charge ratio of 181 and 203 in our final mass spectrum. Let us say we analyze aspirin using electrospray ionization. What would the spectrum look like? We would see something that looks like this. This is a mass spectrum. On the x-axis, we have the mass-to-charge ratio, and on the y-axis, we have something that is called intensity. All intensity measures is the number of ions corresponding to that mass-to-charge ratio. For your purposes, all you care about is whether a peak appears at a particular mass-to-charge ratio or not. In this mass spectrum, we see a mass-to-charge ratio of 181. You can see how that matches our expected mass-to-charge ratio. This peak, this signal, corresponds to the mass of our compound plus the mass of the hydrogen ion. Similarly, on the right, we have a peak, a signal, of 203, which corresponds to what we would expect for the mass of our compound plus the mass of sodium. We call these peaks, the largest peaks, molecular ion peaks. This is because they correspond to the mass of the intact, non-fragmented molecule. How is this useful to us? Let us say that we took our unknown compound and we analyzed it using electrospray ionization, and what we saw were these two peaks. What would they tell us? What these peaks would tell us is that we had a compound that had some mass. Using the mass of the compound, we could then use a computer to establish the molecular formula of that compound. For example, in this case, if we knew our compound had a molecular weight of 180 grams per mole, the computer would tell us that meant our molecular formula was C9H8O4. It would not tell us how those atoms were connected, but this is a great place to begin. Some things to keep in mind. Be on the lookout for M plus H and M plus sodium. In mass spectroscopy experiments, you might see one, you might see the other, you might see both of them. Be aware of that if asked to interpret mass spectra. Let us look a little more closely at these mass spectra. Clearly, there is one major peak, one peak larger than the rest. However, you might also have noticed these smaller peaks to the right. What do these smaller peaks correspond to? Those smaller peaks are a result of isotopes. If you look at the periodic table of elements, you will see carbon has an atomic weight of 12.011. That atomic weight is an average of all of the isotopes of carbon. If you take a sample of carbon, almost 99% of that carbon will be carbon-12. About 1% of that carbon will be carbon-13, and a minuscule amount of that carbon will be carbon-14. How does this affect our mass spectrum? Recall that mass spectroscopy separates compounds based on their mass to charge ratio. Imagine a situation where we have a molecule of aspirin that contains no carbon-13. I have a molecular weight of 180 grams per mole. Now let us say I have a molecule of aspirin that contains one atom of carbon-13. As a result, the molecule of aspirin with one atom of carbon-13 will have a mass of 181 grams per mole, or what we might call M plus 1. How would these combinations of different isotopes affect our mass spectrum? For a molecule of aspirin that contains no carbon-13, we have a mass of 180 grams per mole. We add the mass of a proton to that, we see 181 grams per mole, and that is the largest signal in our mass spectrum. If instead, we have a molecule of aspirin that contains one atom of carbon-13, we have a mass of 181 plus the mass of a proton to give us 182, which we see in the mass spectrum, don't we? Notice how the signal for 182 is much smaller than the signal for 181. That is because carbon-13 is much less abundant than carbon-12. If you look real closely, you can see another even smaller signal at 183. That would correspond to an aspirin molecule that contained two carbon-13 atoms. The take-home message here is that the presence of isotopes will give us different masses for the same molecule. These three signals you see here all belong to aspirin. It's just that some of those molecules of aspirin have different isotopes of carbon. Of course, carbon is not the only element that exists in different isotopes. There are two other elements where understanding these isotopic patterns is very useful. The first of these elements is chlorine. Here I have a molecule that contains a chlorine atom. Using the atomic weight of chlorine I see in the periodic table, I calculate a molecular weight for this molecule of 156.57. Do I see that mass on the mass spectrometer? To make this discussion easier, the mass spectra you see on this slide will not include any ions. Remember that in reality, you would see a mass plus the mass of an ion of some kind, a proton or a sodium. But for the discussion of this slide on isotopic patterns, you will use the mass of these molecules without the additional ions. What I see is a signal corresponding to a mass of 156 and a signal corresponding to a mass of 158. Why is that? Chlorine has two main isotopes. Chlorine can come in a mass of 35, and it can come with a mass of 37. If you take a sample of chlorine, roughly 75% of that chlorine will be chlorine-35, and roughly 25% of that chlorine will be chlorine-37. And you might be able to see how this distribution is reflected in the size of these signals. We have two main isotopes of chlorine. Therefore, we should see two main signals, one for each isotope of chlorine, and they should exist in a roughly 3-to-1 ratio, because the isotopes exist in a roughly 3-to-1 ratio. Therefore, if you are looking at a mass spectrum, you see two main peaks that are 2 AMUs apart. Why 2 AMUs? Because that's the difference in AMUs between the two isotopes of chlorine. That are roughly in a 3-to-1 ratio, you have a chlorine somewhere in your molecule. Very useful to know. Similarly, if I take that same molecule and now replace the chlorine with a bromine, I see another isotopic pattern. In bromine, my two main isotopes are bromine-79 and bromine-81, which exist in a roughly 50-50 ratio. And we see that in the mass spectrum for this compound. We have two main signals that are 2 AMUs apart. Again, that is because there is a 2 AMU difference between the isotopes of bromine. And these signals are roughly the same size. if you are analyzing a mass spectrum that contains two signals, two AMUs apart, that are roughly the same size, you have a bromine somewhere in your molecule. Another very useful pattern to know. That is the end of this webcast. To recap what we have discussed, I expect you to have a basic understanding of mass spectroscopy theory. Know that mass spectroscopy takes your sample and converts it into ions. Those ions are then separated via their mass-to-charge ratio, and depending on the type of ionization we use, we get different information. Electrospray ionization turns our sample into ions by attaching ions to our molecule, the most common of these ions being protons and sodium, although others are possible. Electrospray ionization allows us to figure out what the molecular formula of our unknown compound is. Finally, chlorine and bromine have very characteristic isotope patterns in a mass spectrum. If you see those isotope patterns, you should recognize what type of atom is present in your molecule. Before we finish, a few reminders for the second lecture. You have another series of webcasts to watch for the second lecture. These webcasts will be on infrared spectroscopy. Once you have watched all of the assigned webcasts for Lecture 2, you may choose to complete the optional pre-lecture survey located on the Compass 2G course website. The responses to this survey will help me determine what to focus on during the lecture period. If you decide to come to the optional lecture period, please remember to bring your clickers and the worksheet. And finally, remember to complete the online pre-lab quiz for your first experiment before the due date. If you do not complete the pre-lab quiz, you will not be allowed to perform your first experiment.